Okay, can everyone? Yes, I assume you can hear me. I can hear my own voice, so that probably means yes. Okay, good afternoon, everyone. My name's Aish Fenton. I'm a director of machine learning research at Netflix.
And I'm Jeremy. I work with Aish on our recommendation system.
So today we want to talk to you about why we love Scala for doing machine learning at Netflix. But first I want to let you into a dirty secret of machine learning research. Now, you might think of machine learning researchers as something like this. We're working in a very high complex environment, but we're trained scientists working with precision. But the reality is more like this. A lot of what we do requires a lot of iterative work, a lot of trial and error. We're often trying things really fast, and unfortunately that results in a lot of spaghetti code and a lot of mess in our engineering setups. So why is this the case? So there's a number of things that make engineering quite challenging for machine learning, and they're not particular to just machine learning, but I'd say that they're very prevalent. So number one I'll call out is that numbers have meaning in machine learning. We're working with mathematical objects. So when I say numbers, I mean things like that they operate in a certain domain. But the types that we typically use in the languages that we use, these don't have really any meaning. They're things like primitives, so they're floats and doubles and things like that. So I guess the canonical example of this is if we're working in a particular domain such as log space, when you add two numbers together in log space, that does not equal just the sum of the two logs. That's different things. So this is a number that's imbued with some semantics that tends to get lost with the simple types we use of just primitives. The second one I'd call out is that mathematics is obviously a very rich domain with a lot of structure, and arguably the whole point of mathematics is that we can make higher level generalizations about patterns between things and the structure of things. But when we express this in code, especially fast code, that gets completely lost. So those of you that, I think I'm talking to the right audience here when I say talk about abstract algebra and the beauty of it and some of the higher level abstractions and insights you can gain between things. That is all present in mathematics, but it does tend to get lost once we're operating in code. So the third reason is that we have to write really fast code. So we are always trading off performance for maintainability, and it creates a huge mess. So this was something I randomly copy and pasted from a numeric algebra library, but this is what a lot of the code that we write will tend to look like. It's very procedural, it's very hard to read, but it is fast. And then the fourth and last one I'll call out is that, and I'd say that this is really the dirty secret of machine learning, that we actually spend 80% of our time just gluing things together. A lot of what we do is manipulating data, finding new data sources, new signals, trying to plug them into the algorithms. And we spend a lot of time doing this, and it's where we create a lot of our bugs. So I think when you think, I'd say that when we think of machine learning, we tend to think of ourselves writing the numeric code, the deep learning model, but really that is probably where we spend just a tiny little fraction of our time, and a lot of it's on this giant ETL process around everything that we all plug into that system. So that kind of sets the scene, but now let's talk about why we think that Scala actually helps with a lot of this, and why that's fundamentally an advantage of Scala for doing machine learning. So Jeremy's going to take us through some examples.
Okay, I'm going to kind of stay close to my notes here because this is a terrifying number of people. So the strategy we're going to talk about is to make the type system work for you. And in order to do that, we're going to try encoding some more meaning in the types that we use. And we have two examples here. The schema types is about assigning meaning to things that are normally not typed and reducing some boilerplate in the process. And then I'm going to talk about this idea of symbolic functions. And one of these we actually use. One of them is just a fun sort of side project, and I'll let you guess which is which. But both of these are made possible by implicits, which is kind of, as engineers, it's our hook into the type system. So if you hate implicits, this is probably not the talk for you. So the first thing that I'll talk about is these schema types. And the motivation here is when we're working with data transformation pipelines, it would be really nice to have some type safety. For example, I have some function to aggregate scores. It takes a data frame, it returns a data frame. Well, that's great, but it says nothing about what the input needs to have, and it says nothing about what the output's going to look like. So that's just a recipe for exceptions when somebody who didn't write that function tries to use it. Now, Spark has these typed data sets where it has a type parameter that's like a case class, but we can't be expected to encode every intermediate shape of our data into a case class. That would just be an explosion of case classes. And we also use, at Netflix, we have some complex nested schemas, arrays of structs and so forth, where it would just be unworkable to use case classes everywhere. So we have schema types as kind of a relatively straightforward middle ground. And what we do is we just define some columns that we care about. And these are just sort of abstract bits of meaning that all it represents is an idea of what some column means. And then we'll create a data set to wrap a data frame. This is not Spark's data set. It's hard, naming things is hard. But we're just going to give it a phantom type that describes what its schema is. And it's just going to wrap a data frame. And it has this validate method, which will check at runtime that the column that you said is there, and do some other checks at runtime. And then at compile time, it's going to actually track the type. And we have a few overloads of that. I didn't show them all, but you could use your imagination there. So here's an example of what that looks like. If I wrap a data frame in this data set, then I can validate these columns and say what the physical column name is, and that'll be checked at runtime. And then at compile time, I have some nice type information that I can carry around with that data set. And rather than encoding a bunch of case classes of every possible shape of data, I could just sort of mix and match ad hoc here to represent what's actually in that data frame. And we'll also have this wrapper store some information about what's been validated that we'll use later on. So now this function could be a little more descriptive. It could say, I need a data set with country and profile ID and score, and then I'll give you back whatever you gave me, but I'll add some aggregate score to it, for example. And that intersection type does all the compile work, all the work at compile time, right? You don't even need shapeless for this. I mean, I love shapeless, but it's not even necessary here, because if you pass in something that has, or that's missing one of the requirements, then the compiler will just tell you that's not going to work. But you could also pass in something that has more than needed, and that'll be just fine. And you can add some additional information in those sort of column ideas also. We could have some logic, for example, to validate the data type in Spark. We could have another Scala type that says maybe what our domain level data type is, and maybe some logic to move between those. And then our APIs will be able to use that information to take that one validate call and just do more useful work with it, right? So there's no magic here. We still have to explicitly validate what we think is there in the data set. We're not hitting our data warehouse at compile time or anything to magically infer things. But rather than trying to do magic with it, we're just going to try to do more work from that one call. And we also removed the hard-coded physical column names that were in that function before. And it can just ask the data set, what's the physical column that represents the profile ID? Because that was provided, if you'll remember, when we validated that schema, the user provided that physical column name. And for functions like this, we actually have a data type for them. So it's, call it transform function. It has two type parameters, the input schema that's required and the output schema that will be the result. And we have the compositional methods that you'd expect. For example, and then it takes another transform function that has its own input and output schema and gives you back another transform function that's the composition of them. And we have this type class here that you'll notice schema composition. So this is a dependent type class that computes what the resulting input and output schema are. So it's not as straightforward as just mash them together. Like here's an example of that. So if I have one that takes an A and a B and outputs a C, and I have another that requires a B and a C and a D and outputs an E and an F, then you can notice that the resulting composition doesn't require C, even though the second one requires C, and the reason is because the first one produces that. So we have a type class that will compute that at compile time. And we can also infer some transforms. So if you use the adapted method instead of the apply method, then we can actually go out and search for more transforms that we need to get some of the columns that you might be missing. And this helps us reduce a lot of boilerplate glue, but keep small modular pieces without making the user sort of copy and paste a whole bunch of things that they use every time, because the compiler can kind of do that copy pasting for you. And it works something like this. This is all very simplified, and I know it's a lot of walls of code, but I'm just going to try to get through everything, and maybe we'll have time at the end for questions. So if we just have some type class column provider, it could say that this column B can be provided given columns A and C. We can derive B, and we'll also derive E at the same time. And then if I call adapted, then I don't even have to think about where that B came from. And we actually do this recursively. So if there's a bunch of levels of requirements and produced columns, the implicit mechanism in Scala is perfect for resolving those things recursively. And that just reduces a lot of boilerplate when you're composing large pipelines of data transforms. And of course, if it can't satisfy all the requirements, then you get a nice compile error. Well, it's not a nice compile error, but it's a compile error. And with some extra compositional flavors, for example, you could have a state transform function where it also emits a value in addition to the transformed data set. And that can lead to some really nice expressions of large transformation pipelines. And this is just sort of a contrived example of that. I could say, first I'm going to stratify, and that's going to transform the data set and also give me some stratification statistics. And then I'll generate features. I'll go ahead and train a model, and that's going to give me back the trained model and also maybe score the data set. So that's a transformation on the data set. And then I'll do some ranking, and then I'll run some test metrics, which will just give me back an idea of how good that model is. And then I can output all of those at the end. And then I would have one composed transform function that does all these things and outputs those interesting pieces of data at the end. So it's a pretty simple idea, but it's very helpful for tracking the types and the schemas throughout the entire data transformation pipeline without introducing a lot of burden on the person who's using it. So if we can take this and wrap it up in a nice API and make it kind of seamless, then it works pretty well. All right, so the second thing I want to talk about is this idea of symbolic functions. And the motivating thing here is we like polymorphic functions for math, right? So here's an example with Spire. I could define the logistic function like this, and I just need an implicit trig, which is the thing that lets me do exponential, and it actually also has to be a field, but you can only fit so much on a slide. And this is great. It works on anything with a trig algebra, but it doesn't read that well. And there's also performance implications here with regard to boxing. So you have to be real careful about when you use type parameters. You kind of have an explosion of specialized things, or you could choose to have boxing code instead. And we really can't afford that in a tight loop where we're doing a lot of number crunching. So this is a fun idea for dealing with this, and we're just going to sort of bear with me. I mentioned this idea to Martin at Scala Exchange, and he looked a little bit horrified. And I think that's probably a common reaction, but bear with me. I think it's fun at the end of the day. So we'll start with an expression DSL, and this is probably a pretty familiar idea. But the difference to notice is that these methods don't return expression DSL, they return more specific things. And so we're actually going to build up a recursive type instead of forgetting about anything that's happening. And we have case classes for each of the operations that we're going to support, and we have like an argument case class as well that's going to represent some abstract argument. There's two overloads of each of these methods, and the reason is if we pass a constant to one of these operators, we're going to remember the constant literal type of that constant as well. And here's, and then once we have that, we'll create this symbolic function 1. And that has a type parameter that's a higher kinded type parameter. And if you apply it with some type, then you'll just get that thing filled into the expression. So it doesn't seem all that useful right now, but bear with me. And the constructor for that looks a little gnarly, but really you just pass it a function from an argument to something, and then we're going to figure out what that something means with this unapplied type class right here. And all that does is recurse through and find the arg0 in that type, and then make a hole there instead. So it's kind of like edit expanding that type out. Here's what that looks like. So now I could define logistic as symbolic function 1. I'll say x to 1 over 1 plus e to the minus x. And here's what that type looks like. So it's kind of an interesting type. But what it means is, given some t, this function computes the literal type 1 plus exponentiation of, or exponential of literal minus 1 times that t to the power of literal minus 1. And since that's such a gnarly type, I have a nice little pretty printer for that with fun Unicode superscripts and stuff. So the entire AST of that function is encoded into the type, which might seem completely insane, but really what better type for a function than exactly everything it does, right? I mean, this is the purest function you can get. You literally cannot perform side effects here. And it also means we can do some fun things with implicits. So let's take a look at what that could be. So maybe we could teach the compiler algebra. So I'll just create a type class called simplify, another dependent type class. Given an expression, it will apply a bunch of rules that we're defining down here. And here's some examples of them. For example, a plus 0 is a times 1 is a times 0 is 0, a to the 1 is a to the 0 is 1, et cetera, et cetera. And really, you could have as many of these as you want. We'll go back and add this to our constructor for symbolic function 1. So we're going to take that result type from the function you passed in. First, we're going to simplify it, and then we'll unapply that and make this the function out of the result of that. And here's what that looks like. So if I pass it x to x times 1 plus 0, it just gives me back x to x, which is good. So it simplifies away all the trivial stuff. And this is really only limited by how many rules you're willing to write, right? And how long you're willing to wait for the compiler. But this is actually relatively fast. So what could we do next? Maybe we'll teach the compiler some calculus. So we'll make another dependent type function derivative. It'll take an expression and an x, and it'll give us the derivative of the expression with respect to x. And it's just, again, it's just the rules that you learned in grade school. You know, derivative of x with respect to x is 1, derivative of any constant is 0. You know, the sum of the derivative of a plus b is derivative of a plus derivative of b, and so forth. You know, we'll have other things here like our trig functions and log and exponential and the chain rule and so forth. And it's all pretty straightforward. But we actually need a couple of macros here. I really try to reduce the macros as much as possible, but for some of this stuff, we need them. And this is just a simple a type class that's going to take 2 ints, or literal int types. Everybody is familiar with literal types now, right? Martin mentioned them in the keynote yesterday. But for example, the number 1 has the type int, but it also has the type 1. And so we're gonna use those a lot. And so this type class will just tell us if we have 2 literal ints, what's the difference between them. And here's how we, I didn't actually show the macro implementation, but I think this kind of thing will be easier in Dotty. And so using that, we could implement the power rule. Here's what that would look like. You know, the derivative of x to the p, if p is some integer, is just p times x to the p minus 1 is what that means. Okay, so put this together. We can put a derivative method on the symbolic function. And what it's going to do is it's going to first apply our higher kinded type parameter there with arg0. And again, that's the literal type 0, which would just mean like the first argument, assuming we want to generalize this to functions of more than one argument. So first we're going to apply it with that first argument. Then we're going to take the derivative of that resulting expression with respect to that argument and put it in this type parameter d. And then we're going to simplify the result of that and put the simplified version in this type parameter ds. And then finally we're going to edit expand that ds and get back another symbolic function that's the derivative of the one we created. Okay, so here's what that looks like, and hey, it works. I define my logistic function here, and then I ask for the derivative, and there it is. I figured it out. You'll notice that I have 2 negatives there being multiplied, and they didn't cancel out because I forgot to write a simplification rule for that. So I should go back and do that. But it did find the derivative, and it's correct. But how am I going to use this thing, right? It's just an expression tree at the type level. If I have the symbolic function value, its apply doesn't do anything except its apply doesn't do anything except give me back another expression tree, which is great because then I can call symbolic functions from within other symbolic functions and have the whole thing sort of inlined in the result type. But I also probably want to be able to actually use these things without evaluating a bunch of layers of objects. So that's where reify comes in. We're going to turn the symbolic function back into sort of real code with some more help from literal types. And we need a couple more macros here. I'm not going to go into their implementation, but I'll just name those type classes and kind of use your imagination as to what they do. And it's all pretty straightforward. And I will post the POC code later today if you want to see how it all works. But here's kind of what that looks like. So we have a dependent type class again called reify, and it takes an expression in some t that we want to pass into it. And the instances of that are pretty straightforward. So The first one here, arg, that's just saying that the first arg0, is going to expand to be x0 in code. And a constant is just, it's going to be itself in code. And to multiply two things together, if they're, the reason for any val numeric there is to say that this is for primitive numerics. Because I know all those have a times operator, so I could just mush them together with the times operator in between, and I've got valid code for that expression. So that's kind of like our algebra, but all it does is witness that I can reify an expression over a given type. So for every expression operator that we want to use, we'd have to have a reify instance for any given type that we want to use. But we can make that be different for different types, which could be interesting. And here's an example of what it looks like if I reify this expression over doubles. I get this code, which looks like pretty much the, pretty much the quickest way you could probably do that in Scala. Okay, and then we need one more macro to take that code, and you could guess what that macro is going to do. It's going to take the code, and it's going to actually emit a function in Scala that inlines that code in the function, and the result is going to be a specialized function over doubles that does whatever was in the symbolic function. And again, I'm not going to put up yet another wall of code for that macro implementation, but it's pretty straightforward. And here's kind of what it looks like all put together. So this is a REPL session, and this is 2.13, so I can have literals there. So I created the logistic function, and I found its derivative, and then I'm going to say toDouble operator, which will reify that into a specialized Java util function double operator. And then I spit out the disassembly of that so we can see that, yes, indeed, it is specialized. It does pretty much what you would expect it to do, and it should be relatively performant. Okay, so just as a reminder, this all happened at compile time in contrast with some there's other staging mechanisms kind of like this that are partially at compile time and partially at runtime. So this was all at compile time that we took that symbolic function, we found its derivative, and then we turned the derivative into a specialized function over doubles, all at compile time. And again, if I implemented the instances, I could use that for other types as well. And we can trivially extend that to symbolic functions of more than one argument. So that's why we had that int type parameter in the arg expression DSL, was so that we could have arg0, arg1, arg2, etc. It's a little more work, but we could also extend this to functions over vectors. The calculus is a little more complicated, but it might be worth it to get specialized gradient computations materialized at compile time. I think that would be pretty cool anyway. And it also gives us an opportunity to optimize based on what the type is that we're working with. So you could imagine if we had a matrix type, for example, our reify instances for that could look ahead into the expression tree to figure out, hey, what's the optimal series of BLAS operations to do this computation. So there's a lot of opportunities there. And is this a zero-cost abstraction? I mean, not exactly. There was that object hanging around that represented the expression tree, but it turns out you don't actually even need that value. All you need is this type, and as long as the compiler has the type, you can materialize the function out of thin air, basically. Yeah, so it's kind of fun. And I will post the code of this to this URL later on. I haven't done it yet because I was frantically scrambling to finish this presentation, but I promised to do that. And it's a little bit rough, but it's fun. And the takeaway that I want out of this is that people think about what problems you could solve by moving more information into the type system. Because a Scala program is really two programs. So there's a program that happens at compile time, and the result of that program is a program that happens at runtime. And the more computation you can do once at compile time, the less computation you have to do many times at runtime. So Yeah, you know, the other takeaway is whatever crazy use case you have that that Scala wasn't even thinking about when it was designed, you can leverage the type system to make some of those things a reality, and then wrap it in a nice API, and it'll blend seamlessly with all your other Scala components. So that's what I love about Scala. It gives you the power to do these things. And it's not always pretty, but you know, the power is there, and I think that's pretty unique to Scala. All right, so just a little peek at some of the things that we're looking forward to in Scala 3 to solve some of the problems that Aish mentioned. So opaque types, those are going to be huge for us because we can give more meaning to our data without any performance penalty. So that's going to be huge for us. I mean, I don't know, I don't care what Martin's poll said, that's going to be a game changer, I think. And there's also some other interesting features that you know, maybe other people have touched on, but principled structured types, you know, maybe that will end up being a better way to do the kind of ad hoc schemas that we were trying to accomplish with those phantom types earlier on. So that could be interesting. The meta-programming story looks a lot cleaner in Scala 3. So a lot of the ugly macros that I had to use for my harebrained scheme earlier will look much nicer and much more comprehensible in Scala 3. And the cleaner dependent types, meaning that, you know, an implicit can refer to the output of a previous implicit, will let us throw away a bunch of those extra type parameters that we had hanging around. So if you remember, I had like you know, an R and a D and a DS, and each implicit's subsequently filling in one of those. You won't really need those anymore because of that machinery. So I'm looking forward to that. And it's just more ways the type system can work for you, which means more reasons to love Scala. And I'll turn it back over to Aish now, and he'll talk about some of the things that are on our wish list.
Yeah, this is very much our wish list, and we did some brainstorming about trying to answer the question, well, if Scala is so great for machine learning, why don't you see a lot of machine learning researchers, data scientists using it, especially compared to Python? And really a lot of it came down to some key tooling that's missing. So we cheekily really put together a wish list of things that we wish were built, and I think would really help the adoption in the machine learning community. So one of the big ones is a great notebook environment in Scala. So as researchers, we spend a lot of time working in Jupyter and tools like that to do this kind of visual REPL type environment. It's just a very natural way for us to do our work because a lot of what we're trying is very iterative in nature. Often we need to visualize it too. Now there's some projects that are being worked on at the moment. I think there's some really interesting things with metals being looked at with being combined with Jupyter, so that's promising. And there's some other projects that are on the horizon as well in this space. But I think at the moment we just really look forward to those maturing. A simple one, but absolutely required, we need a good plotting library. There needs to be a way to visualize what we do. In the Python world, they use matplotlib. I'd say it's a pretty ugly library. The API is pretty awful, but it's comprehensive. And in Scala, there just isn't anything that's got a great comprehensive set of visualizations. NumPy is an interesting one. So when I reflect back about why has Python been such a success for machine learning, one of the things that occurred to us was that NumPy, so if you're not familiar with NumPy, NumPy is a multi-dimensional array library. It came out early in Python, and it became the de facto standard. So if you wanted to have an array with multiple dimensions of data, it was just the go-to tool. And because of that, it became the lingua franca of data science and machine learning. And it gave us a way that we could, in Python, have many libraries that were speaking the same language and had the same types, essentially. And in the Java, JVM, Scala community, we're still missing the one true multi-dimensional array library that we can all know we're communicating the same way, that you can rely on that type. So I think that that's a missing bit there. There's things like Breeze, but that has some performance implications, and last time I checked, it wasn't actively developed. There's numerous Java libraries that wrap lower level primitives like BLAS. They're also very good, but the community is just extremely fragmented in this space. So it makes it hard to publish a library where you have an API that requires a multi-dimensional array. And the last one is there needs to be a good story around wrapping C++. Unfortunately, we can't get away from C++. Maybe in the future we will be able to, but at the moment there's still just so much stuff written in C++ that we need to wrap. There needs to be a good story for doing that easily. There's some great stuff on the horizons with that. We're looking forward to Grail VM. Still got some question marks over whether it's really going to solve the whole problem there, but looks really interesting. There's also a number of JEPs in progress with Java that try to address this, kind of rebuild JNI from the ground up to make it more compatible and more easy to pass data back and forth out of the JVM into the native substrate. But that's still on the horizon, and the time frame's sort of unknown, and then there's Scala will have to support that too. So that's still a missing piece of the puzzle. But I'd say the largest bit that's missing is you guys. We need the Scala community to take an interest in machine learning and get excited about building some of these tools and tackling some of these problems. I'm a firm believer that some of the engineering talent working in the Scala community is some of the best engineering talent available. So I think if I can do anything, I want to get you excited about machine learning and about data science and get you excited about building some of these tools and tackling some of these challenges. And if I can do that, that's really a success for me. So yeah, on that, I think we'll end. I don't know if we have time for questions.
We do. I rushed so quickly through my slides that we actually have several minutes for questions.
Yep.
No? All right. Thank you.
Coming.
Thanks. In the list of things that you mentioned we need, you didn't mention a sort of data set, data frame, API. Do you feel that's because you have a sufficient replacement of what you've done already? Or do you think that Sparks is good enough? Or do you think we need something there?
I do think Spark does a good job. So I guess in the Python world, people use pandas. I think Spark, so there is one thing missing in Spark. I think the data frame API and the tooling around that is actually really good in Spark. It's very intuitive and very easy to pick up. But I wish they had an abstraction there that meant you could also use it locally on data. It didn't have to be distributed. But that aside, that wouldn't be top of my list because I do think Spark does a good job with it.
Okay, thanks.
Hi. You designed a solution to, in a sense, check schemas at compile time for data frames. Have you ever tried frameless And what are your reasons? I have my own reasons not to use data sets, but what are your reasons not to use data sets?
That's a good question. Yes, I'm intimately familiar with Frameless. Um, I think there's a little bit more machinery that Frameless requires, and a lot of the consumers of our API are not Scala experts, and when they'll see something that requires all these dozens of implicit arguments to prove things about the code, it can be a little intimidating, and I think that's one of the reasons we don't really use Frameless. I think it's a really cool project, but there's some other shortcomings that we just needed, like a little bit more of a relaxed middle ground, I think. And the scheme that we've came up with solves it pretty well, because it's flexible enough to give us the safety that we need and a little extra information from that, but still have escape hatches sort of for when things when the user needs to say trust me, we have escape hatches for that. Does that make sense?
Yeah, so the question was, what about data sets?
So the Spark dataset API is what you're referring to. Yeah, that I kind of covered the motivation around not using that, but it would just be an explosion of case classes to address every combination of columns that might appear at some point in our transformation pipeline.
Yeah, a lot of the workflow of machine learning is we iteratively build up the schema over time. So it's not like it's transforming from A to B. It's a much more kind of gradual process as it sort of morphs between the two.
Just a very quick question. I saw that you called your library Baudrillard. I just wondered what the background for that was.
Naming things is hard, but I guess the idea was that, is it a program or is it a type? Maybe at some point, at some level, what's the difference? And that the reason I named it after Baudrillard was a sort of parallel to the idea of, are we a universe or are we a simulation, and maybe at some point, what's the difference?
It's deep.
Hello. It's pretty cool that you built, and I wanted to tell, could you tell a bit more about how your experience verifying that it's correct and debugging it?
So when it comes to macros or implicits, or which aspect?
The whole design.
Well, implicits are pretty trustworthy. If it's not going to be correct, it probably won't compile with implicits, assuming that you've defined everything correctly in the rules that you made. So that's less of a worry. If you get the wrong result, then you can usually poke through your rules and figure out why. Macros are kind of a difficult thing to become an expert in, because the APIs are not very well documented, and there's a lot of internal quirks that you just have to encounter before you kind of blunder your way around into getting around them. One thing that helps a lot, I think, is in IntelliJ you can actually connect to an SBT session where your code is running, and then actually put breakpoints inside the macro and see what's happening. That really helped me at least learn kind of the learn the ropes of the macro API. But fortunately, that's all going away, and the macro system in Scala 3 is completely redesigned and looks a lot cleaner and has more parity with actual code. So it should be a better story around that. Does that answer your question?
Sorry. Regarding schema types, if I understood correctly, user code refers to columns using types. That means having at most one column of each type in a data frame. But in my experience, it's natural to have several columns of one type and sometimes using joins, for instance.
Right, and that's why the columns or the columns that we were expressing in our schema type are more about the meaning of the column rather than like the data type. So those weren't data types. Those were like, I have a column that represents the profile ID or the video or the features or etc. And it's not as common to have two columns that mean the same thing that have different values. Yeah, I mean, that being said, if you did have that situation, you could just create a new idea that, you know, if I have two columns that are both profile IDs, what do each of them mean, and make a more refined concept about what that meaning is. So that it was about encoding little bits of meaning into the type system. Does that answer your question, or not really? Okay. But we'll talk about it afterwards.
Hello guys. I'm here, Pavel here. Hey, last summer I met with my colleague who is working at data engineering department in LA at Netflix. And we were talking about vertical content development. And in the regard of that, I have a question. What is the very next step, big step, combining machine learning and Scala at Netflix? I'm talking about more perspective, less technology, more kind of strategic. If I may ask this question, of course.
Yeah, sure. Boy, I wouldn't say we have anything kind of as grandiose as a strategy. I'd say that we're quite happy with what Scala provides us. We use a mixture of Python for a lot of the modeling work because the ecosystem is so rich there, but Scala for everything else around it. And we're quite happy with that combination. So yeah, I wouldn't say we kind of have a strategic initiative or anything to try and change this. Personally, I'm a big fan of Scala, so I would love to see it get richer and more adopted in this area. But I'd say our efforts are sort of a little bit more tactical. As we come across problems, we address them and solve them and put resources behind them.
Hello? Oh. I was curious about your symbolic type. So if I understood correctly, that was kind of an interesting thought experiment, but it also felt like it was valuable because while it was difficult to express, you could write it once and then, you know, you can use that, I guess, like a library to make like the machine learning aspect easier. So like how far did you take it, or like why did you not try to take it further?
Okay, so I'll spoil it and say that one was the research project and not the one that we actually use, in case anybody didn't guess that. So why didn't I take it further? I mean, it's so in versions of Scala prior to 2.13, it was very difficult to express some of the things that kind of relies on. So I had implemented it before, and it was just kind of ugly. And it wasn't until 2.13 came around that it really kind of cleaned up a little bit. And yes, that was the cleaned up version that I was displaying, if you can believe that. You know, why not take it further? I don't think there's any good reason. I kind of think it's a cool and useful thing that you know, maybe it's a little bit strange to do like a version of Spark CodeGen, but in the type system. and it's probably not the ideal way to do that at compile time, but you know, the reason I haven't done more with it, I think, is because I'm not sure anybody would use something like that in real life, I guess is the honest answer.
I can kind of give you my end of that as someone that would be more on the user end of it. So I think the gap would be support for GPUs and that kind of extra level of effort and work that needs to go in still about really highly optimizing it for computation on GPUs or vectorized code or that type of thing. So what we mostly use for this auto gradient type work at the moment is things like TensorFlow and PyTorch. I think as languages, they're actually have a severe deficit in the language to be able to express these things nicely. But there's been big investments on it and people have written highly optimized underlying GPU and C++ code to make it really fast, and that effort's gone in. I think starting from Scala would be a much better place to start from because we can do the things that Jeremy showed us, but still there needs to be that work of someone to go in and really write that performance optimized code.
Yeah, and I think another reason is that that obviously, I mean, both of those things that I showed rely a lot on type inference. Like you wouldn't want somebody having to type out one of those big schema types, or type, God forbid, type out the type of that function, of that symbolic function. I kind of blame IntelliJ because they have a default setting that hates type inference, and anywhere you use it, it says that your code is wrong, or it says that you know, your style is wrong, or whatever. So that's a perception that kind of blocks interesting things.
Hi. Besides using Scala to implement ETL pipelines, do you also use Scala to evaluate your model in live online systems? And in general, do you think it makes sense to strive to reuse some code between two worlds, like offline training on online evaluation?
Yeah, I'll take the first stab at that. Yes, absolutely. In fact, I'd say that that's one of the big advantages for us of using Scala. So our setup at Netflix is that we mostly, the teams that we partner with, mostly run Java in production. We have a very heterogeneous environment in the back end, offline though, in terms of modeling. Really with modeling, it's sort of anything goes. It depends on the scientist. So we need a way to be able to share these offline components in with the online teams. And that's why that was one of the initial motivations for us about really getting into Scala, was that we felt that if we could express a lot of the feature engineering work that we do through Scala's API, that it would be A, much more expressive, but B, it would be something that we could have run offline, but then deploy it in a jar, and the online Java systems could also run the same code that we are using offline to produce the models and to do the research work. That's it?
We're out of time.
Okay. Well, feel free to come and chat over lunch too. Thanks very much for listening to us.
Yeah, thanks everybody.